Wait a second. Yeah. Yeah. So the function is equal to 1 when it's smaller than 1/2, and is 0 when it's larger than 1/2. And the Fourier series is used to represent a periodic function. But in here, the fx we define is only have a range between 1 to 0. So we need to extend the function f into a periodic function, so we can use Fourier series to represent it. So when is pt 1 and 0, and 1 and 0 is has have like this, and how we do it is with that fx is equal to fx plus 1 here. So it will repeat itself again and again. So so in part A, we need to represent it by Fourier cosine series. First, the series like this. It has a constant coefficient plus a summation of cosine function. And so the equation for the A naught is equal to this 1/2L time integral with upper bound capital L and lower bound capital L. And what inside the integral is the function. And here the upper bound and the lower bound is representing the whole period of the function f is here. And because the upper bound and lower bound has the same value, so we take the range from here to here. So the L is equal to 1/2. And because when s is from negative 1/2 to 0 is equal to 0, so we only need to integrate half of it. And you'll get the A naught is equal to 1/2. And then we calculate the coefficient AN. The coefficient AN, we can use this equation to find it. And be careful about the coefficient at the beginning. That is not 1/2L, but 1/L. So, and again, because we only need to integrate half of it, and another half is 0. and then you will get 1 over n pi times sine n pi. And sine n pi, because the n is a positive integer, so sine n pi is equal to 0. So for all coefficient an they are all equal to 0, except a naught. So if you draw a graph according to the using Fourier cosine series to represent it, you should get a curve that has a constant. They have the same value across the whole map. There's 1 over 2. And in part B, we now need to represent the function f with sine series. And the function is just a summation of sine function, similar to part A, but it don't have a constant coefficient here. Oh, yeah, don't have a constant term. And then we do the same thing to find the coefficient Bn. And then we put it L equal to 1 over 2. Again, the second half of the integral we don't need to calculate because it's 0. And after integration, you will get this, and oh, it should be cosine here. Yeah. With negative sign. So you get a cosine n pi plus 1. And cosine n pi is equal to negative 1 with a power of n. So the Bn is actually equal to n pi or 0. And when n is odd number, and is 0 when n is even number. So if you pick a large n and then you use this coefficient, this equation to plot a graph, you should able to get a graph like this. And this is a square wave, and if you combine what we get in part A and part B, that's That is the dashed line is what we get in the part A. That's equal to 1/2. This part here, they cancel out each other, and this part they add up each other, and it will become the fx that we define in the beginning of the question. So if you want to represent any function, you need a sine function and cosine function to do it. Except for odd function and even function. That is the case mentioned in the lecture notes. So let's move on to question 2. This time there is a function fx that we need to Fourier transform is equal to e over x times e to the power of negative x, and is for x larger than 0 and 0 for otherwise position. So there is two ways to do it. According to the definition of Fourier transform, that if we want to transform function fx is equal to equation like this. The first way to do it is just simply using the integration by parts, and from 0 to the negative infinity is 0, so we don't need to calculate it, and you get a the exponential term will become 1 plus negative 1 plus ik times this here. In here, we do integration by part. And the first term inside the brackets is equal to 0. So only the second term left. And this integral is very easy. and where x is infinity is equal to 0, and where is 0 is equal to 1. So the final answer of this part is this. There is 1 over square root of 2 pi times 1 over ik plus 1 square. So this is the first way to do it. And I'll give you 5 more minutes to jot down, then I will teach the second method. So the second method is kind of look like what we teach in the Laplace transform. There again, we start from the definition of the Fourier transform, and I just use the part of the result in method 1. So I make a little rearrangement here that I multiply negative I and divide a negative I here. So you will have this. You have this here. And then we do a little trick inside the integral. That we combine the negative ix with the e to the power of negative ikx here. That this part is actually partial differential with respect to k of ikx here. And because of the integral is with respect to x, so we can take the partial differential with respect to k out from there. And then we just integrate this part. And this part is just the last part in method 1. And you will get a 1 over 1 plus ik. And then we differentiate with respect to k, and then you get this. Yeah. So, and then you will get the same answer from method 1. So this part, if the differential with respect to k, we can generalize it into a form like this. That's if we know any function, arbitrary function gx, we know what it looked like after the Fourier transform. we can also know the Fourier transform of xgx. That is u to I 1 over negative I differentiation of gk with respect to k. So there's two methods depending on what you want to do. What method you more comfortable with, and you can choose whatever you want to do to finish the question. And this method can apply to a high order term of x here. So